G'day chemistry students. Today we move into our reactions with metals part 1, which is all about corrosion. There'll be one more video to follow afterwards. In particular, we are focusing on dot point 3.2.1. Let's get into it. In this one, we're going to be looking at corrosion, which more commonly known as rust. You'd probably be most familiar with the rust that forms with iron, which has that really classic orangey brown kind of color. Here we see an anchor that's rusted over quite a lot, a gate as well, which is rusted over exceptionally. It's got lots of divots and craters and all sorts of interesting shapes going on. But as well, other metals rust too. Probably the most notable or remarkable one that's quite common from day to day you may see is copper. Best example being the Statue of Liberty, which originally was just plated with solid copper that had that browny, orangey, metallic copper color to it, with the intention that quite soon it would completely corrode, and when copper corrodes, forms quite a beautiful greeny turquoise layer on the outside. So yeah, that's the Statue of Liberty that we see today and has looked like that for decades. Now, in particular, there are different kinds of corrosion reactions. One thing that I will say, I didn't define this at the top, is that corrosion just in general can be defined as a process, or corrosions of metals in particular breaks down a metal by some sort of physical or chemical mean. There are corrosion of other substances as well. Generally, when we talk about corrosion of other substances, we're mostly focusing on the chemical breaking down component though, but physical elements can come into play when we look at corrosion too. In particular, what we're going to be looking at first are reactions with metals and oxygen and water. This first kind of corrosion forms some sort of metal salt of some description. And the process is quite complicated and can form multiple products, but I've kept it simple for the moment. What I will say is that if a metal is reacting with an oxygen and oxygen only, it will form some form of metal oxide. Now, keep in mind this is very similar to the combustion process that I looked at a few slides ago when we were looking at our synthesis reactions or our combustion reactions, where we were looking at the formation of magnesium oxide. This can be categorized as a corrosion process as well if it's happening really slowly. In particular, if you're just leaving the metal out in the presence of oxygen without sort of initiating that reaction, it can still form an oxide really slowly over time. The other reaction with water is significantly more complex. I've given a TLDR version, just a simple reaction equation to sort of summarize the multiple steps that rust or rusting with water can take. This one in particular is for iron. When it reacts with water and oxygen, it ends up forming this product over here, which is iron hydroxide. As I said, different products can form as well, and the process takes multiple steps, but you're more than okay just working with this definition for the moment. Now, in particular, when corrosion is happening, there are a few ways to speed up this process, especially when oxygen and water are the only things reacting with the metal. Now, the things that are here in this orangey red color are chemical factors. So things like pH, acids or bases, can have an impact on the rusting process. Water temperature as well can speed up the process too. Dissolved oxygen or carbon dioxide can also play a part in speeding up that corrosion process. Other dissolved solids can also do very similar things, as well as bacteria that may produce chemicals that assist with corrosion as well. Not all bacteria do this though. And then the bits in green are physical processes, things that would wear away an outer layer of rust so you can continue to corrode the metal that's underneath. So things that essentially would erode away the rust. Flowing water, solids that may also have collisions, anything that would erode or move or break apart that rust and reveal the metal that's underneath. We can also have metal-acid reactions, and the general equation for this is that if you combine a metal and an acid together, they will react either fast or slow. It depends on the metal itself, but they will eventually form salt and hydrogen gas. And I've got some examples down here, both involving sulfuric acid, H2SO4, and hydrochloric acid, HCl. And you can see the form of the equation that's taken up here with a few different examples of metals. Notice as well that they've also been balanced accordingly, both to ensure that the salt or the equation of the salt follows a correct empirical formula based on their charges, as well as the coefficients out the front, which change with the number of molecules to make sure that the conservation of mass is maintained. If we were to form hydrogen gas, we can actually test for its presence by completing a pop test. So by building up enough hydrogen gas, say in a test tube, if we were doing a reaction that produced enough of this gas, we could capture it and then quite quickly release the seal that we've got over the top of the test tube, put a match to it, and it should make a pop. Essentially, we're doing a miniature explosion. Thank you very much, everyone. In the next one, we're going to be looking at another set of reactions with metals. This one is a metal displacement reaction where two metals essentially swap place, one going into solution and another coming out of solution and forming a solid. But until then, have a good one.